So here's my picture. I have something that doesn't want to rotate. Try again. Okay, so I have a joint Gaussian distribution. I am looking at 3 random variables. We're looking at 3 random variables that are known to have a joint Gaussian distribution, and I requested that this be a Gaussian process, so it means that each subset also has to have a Gaussian distribution. So if I look at any 2 random variables, they also have to be Gaussian. Now you see this is a funny shape. Even, okay, there's an angle where there's a little bit more light. I put the light in a bad position, I think. It's very dark. But you see that this is a joint Gaussian distribution, and it is somehow has a funny flat shape. Or we also see there's some correlation. And, well, why is that so? Because I used a covariance function that gently decayed with distance. So it means my point x1 is positively correlated with x2, and it's a little bit correlated with x3 because x3 is further away. So again, the situation I consider is here x1, x2, and x3. And I used a function I think I used the RBF kernel here. So this means that between x1 and x2 I have a lot of correlation, between x1 and x3 I have a little bit of correlation, as measured by this function here, and so on. So I filled my entire covariance matrix by the corresponding values. Okay, so here for distance of 1, I get this much, or I predict this much covariance. For the large distance, I have a much smaller value. So I can now assemble my entire covariance matrix by entering these values of my function. And when I do that, and when I plot the resulting Gaussian, I get the isosurface that you've seen rotating here. Now, I'm entering observations, and this is what this plot is all about. So I am conditioning on the observation that x1 should have the value 0. And this is why you see I've cut a plane through my Gaussian. So I'm conditioning on the fact that x1, my variable x1, has been observed to be 0. So I'm cutting my 3D Gaussian, and I'm left with just a 2D Gaussian that lives in this plane. And now I am, in addition, conditioning on the fact that x2 has the value 1. So I'm cutting another plane, and I'm left with just a single degree of freedom where these 2 planes coincide. And it so happens that these conditional and marginal densities for Gaussian are always Gaussian in themselves. So along this line here, I also have a Gaussian density. And I'm now switching off this ball so that you can see it a little bit better. If I find it. So we have a Gaussian distribution, a 1D Gaussian distribution here. And this 1D Gaussian distribution corresponds exactly to my conditional estimate, or to my posterior distribution. This is my posterior distribution given the prior. So the prior was this 3D Gaussian. Then my observations my likelihood was given by these two observations, and I can thus compute this posterior distribution for the third point. And well, by looking at the plot alone, so x3 is this variable here, you would see that, okay, I would predict a pretty large value. I would predict a pretty large value, and you can also see how big the standard deviation around this value is, or would be. Now you also, I think, will start to see why we can have overshooting in these models. Because if I use, so what do I mean by overshooting? I also have it in the presentation somewhere. So if you look at this plot again, my observations here were, I think, 0, 2, and 1. But my prediction takes values larger than any of the ones that we have observed. So my prediction, it's really an extrapolation. I'm saying that I predict that in between there's a larger value than anything that you've observed. That's a quite courageous, assumption to make. This only happens when you use a very smooth stochastic process as an assumption. Now, what does this mean in terms of our picture here? Can you try and explain? What does it mean to have such a very smooth stochastic process? You can explain almost everything in terms of this picture here. That's why I like it. I'm trying to look for the best angle here. I'm really sorry for the camera light. It's in a bad place. So, your turn. Let's use two different kinds of functions here. One that decays very quickly with distance, and one that decays very slowly with distance. What would this three-dimensional Gaussian look like? Let's start with this case here, where our covariance function decays quickly with distance. Yeah, I see a good gesture there. It's the shrink, no, because you see the variance stays the same. So along each individual axis, I have the same spread as before. No, we assume that the mean is 0 in both cases. So it's still centered at the same place. So, yeah, the angle, but more than the angle, something else. Yeah, easier. Come on. Yeah, it becomes more spherical. So if you take the extreme case of a function that decays very, very quickly with distance, let's look at our covariance matrix in this extreme case here. Our covariance matrix would be, I'm assuming variance of 1, okay? And we would have practically 0 everywhere else. Because at a distance of 1 here, my covariance has already gone almost to 0. Now, this is the covariance function of a ball, or of a totally isotropic Gaussian. So in this extreme case, it would become a ball, and well, what would be our prediction for the third point? So again, the first point was assumed to be at 0. The second one, there was an observation at 1, or was it? Yeah, I think it was 1. What would be your prediction for the third point in this extreme case? Yeah, so your prediction here would be almost totally at 0. It would be a little bit above 0, but almost 0. And in between, our function would look like that. It would essentially be a function with such a quickly decaying distance covariance. It would be a function that has a brief excursion to explain each observation that you see, and it would then immediately return to 0. That's right. Okay. Now, how about the other extreme case where the covariance function, let's make it more extreme, where the covariance function decays very, very slowly with distance. No? Can we talk first about the shape of the Gaussian? What would happen to the Gaussian? If it becomes very, very highly correlated. So if we decrease the correlation, it became a ball. What if we increase the correlation? Yeah, it will. In the extreme case, it will become like it will approximate a plane. It will become very, very flat. Yeah. And now, if you and here we have a sort of intermediate case. It's not a ball, it's not a plane, it's something in between. And if we now look at the way this beast here is tilted, you see that it has some tilt, or I hope you see. Well, I think you see it here. It has some tilt in this direction. And this tilt, or let's look again at the presentation here where I've switched off the ball. See, this is the tilt that I observe in the one conditional density. This is the tilt that I observe in the other conditional density. And if I now turn this into if I make my Gaussian thinner and thinner, they will meet further and further up. And indeed, the limit here, I think, would be I think the angle will also change. So I think the limit here would be a function that you said 2, huh? I think that's about right. Huh? It would do something like a linear interpolation here and then shoot up further, then eventually come back to 0. Yeah. If you have a 0 where? There. Yeah. So what's your question exactly? Let's or I am your. So you have 3 points, yeah? And so what are the labels that you predict? 0, 1, 0. And where do you want to make a... Okay, so let's say for... yeah, anyway. So if we now assume a very smooth process, I think it must do the following. It will become pretty... if I now use a Gaussian that decays slowly and without a nugget, we would get almost something like a kink here, and it would slowly decay back to 0. And we would get, it's symmetric, so same in the other direction. Would continue here. You can produce very interesting effects. If you do the following, you can try that in your homework. If you do the following sort of, let's say you take 2 measurements which are close by, and you take a covariance function that's very smooth, like the RBF kernel with a big standard deviation. And if you choose, let's say, an observation of 0 here and an observation of 0 there, and then something large for the third observation, you get out very extreme predictions. So something that will go deep into the minus and then come back and go very far into the plus and then eventually return to 0 on both sides. And by the way, in this case, your covariance matrix becomes almost singular. You will have, it will almost become rank deficient. So this tells you that, or it is already an indication, well, that the model is not going to be very stable. And luckily, in terms of this model, you can also ask, so it will always give you a prediction, but it can tell you how painful the prediction is. And a measure for, if you get very little density here in your area where you intersect all your conditions or your measurements, then you know that this is very unlikely to happen under the prior that you put in. So nobody can argue that these are your observations, but then perhaps you're not using the right model. Okay, so this was all in terms of pictures. And after the break, we will do the same in formula. So let's do the math. And I think this is so what we're going to look at are established and famous results. But they're so established and so cumbersome to write down that in most, papers and books, it says, as it is well known, and then there's a reference from the 1960s, and then you're left alone to find your 1960s book. And if you want to verify, if the result hasn't gone wrong in the last 40 years or something, it hasn't gone wrong, of course. But I want to give you the explicit formula, even if it's, going to be many symbols. Let me see my ink. Okay, I have enough ink. Okay, so we want to find the parameters of this posterior Gaussian distribution, and we need the mean vector. And Bernhard, could you please switch over here? And sorry, and the covariance function. And I'm following Lauritzen here in doing the math this particular way. The proposition is that if we have a random vector, so we used capital letters already for matrices, so I'm now underlining it to say this is a random variable. If this random variable is distributed as such, then the marginal is given by, or is distributed by that. So in other words, we don't need to do any complicated math. If we just want to integrate out part of our random variables, then we can simply use the corresponding parts of our partitioned mean and covariance vectors and matrices. Okay, now comes the more difficult part. We are interested in the conditional distribution of y1, given that For our random variables y2, we have a realization y2. And we're calling this mu 1 given 2 and sigma 1 given 2. And now comes the claim, namely that mu of 1 given 2 is the following. My notation here is not great because before I used the capital letter for y and now there's a small letter here. So to avoid too much confusion, let's just say that this here is so the part number 2 of this partitioning here. Part 2 corresponds to the training set, and part 1 corresponds to the set of query points. Now, both of these will look familiar to you. We had a few slides back the formula where I had written this result for just a single query point. So I'm using a different color here. So we had sigma squared minus lambda transpose sigma 2, 1. So this part here, this part corresponded to lambda. And there we had assumed the mean to be 0, so the first term was not there. And the second term was k, we've seen an expression before, k times k minus 1 times y. So, you know, we're, as I said, we're taking 3 routes to the same goal, so it's not surprising that we've seen equations like this before. Okay, and now I want to prove these 2 results here. And for notation, I'm going to use the letter P, because normally I call the precision or the concentration matrix K, but K in our case is already taken for the kernels. So now I'm calling it P for the precision matrix. Okay, now, as I said, it was not invented by Lauritsen, but I'm here following the development of Lauritsen 1996. This was one of the first books on probabilistic graphical models, and what I'm saying now is somewhere in the appendix. So we are looking at the distribution of the response at the query point given the responses in the training set, and by Bayes' theorem I can can rewrite it as follows. These mu's and y's are difficult for me. Okay, this was the first term, and now we have the second term. And the goal is to now express all of this in terms of what we know. And what we know is we want to express it. We want to get a probability density for our query variables. So I want to express it in terms of these query variables here. Now, I will write down an abstract term, and then we will see how we can translate one into the other. So what I want is, I'm omitting the exponential y1 minus mu of 1 given 2 transpose So this is what I would like the argument of my exponential to look like. And I'm multiplying it out. So we have a term that's quadratic in y1. Okay, and I now want to somehow relate this, which is just written in stylized form, because these things which I'm underlining here are not yet known. I want to find out what they are. So this was just in stylized form, and I want to now compare this to the top row here. And I'm starting with the term that is linear in y1. So we compare the coefficients, and the term, or let's say the coefficient of the term that is linear in y1 is the following. In the case of the matrix up there, see we have a y1 here and not on the other side. So this is what I'm looking for. And then down here, I still have a mixed term which is also linear in y1. And I can rewrite this by multiplying out this P11. So I'm saying that this is the same as mu1 transpose. I'm multiplying out this guy here. And all of this is an effort to complete the square. Okay, so next I need these terms or these elements of the precision matrix. And for that I'm using the matrix inversion lemma, which I'm going to show explicitly, and I suggest that you don't follow me in... Was this too fast? Have you copied everything you need to? You can just watch me sweat. And I don't know how to prove it, but let's check if it's true. Yeah? So this lemma says that my precision matrix, which I have compartmentalized here, in fact we are symmetric, so I could write A, B, B transpose C, but I'm using the general form of this lemma here. And I will say in a moment what D, E, F, G are in the first place. With the following: E is A minus BD to the minus 1 C. Okay, and we are simply, or I'm simply going to insert, so this is the matrix inversion lemma, and I will now simply invert EFG in this formula and then multiply the horrendous thing with ABCD, and then we see if the identity matrix comes out. So e to the minus 1, rewriting it is the following. Then minus e to the minus 1g is and down here minus f e to the minus 1 is and finally we have here the d minus 1 plus d minus 1c a minus b d minus 1c okay, and I'm now multiplying this with a, b, c, d, and I want to show that this gives the identity matrix. So we can do speed multiplication as a new sport here. So I have this term minus that term. Something similar here. then down here we have okay, in the final term, okay. So let's see what we can do about this. Here, in the first term, I can multiply out what I have on the left-hand side. So if I multiply it out, it's this expression to the -1 times a minus bt minus 1c. And that's exactly what I had in here. So this will give me the identity matrix for the top left corner. That's already very good. Then here d minus 1 times d is the identity matrix. And then well, this term is the same as that, but they differ in sign. So I can cancel these two, and I find a 0 for the top right corner, which is also a relief. Now how about this one? I can multiply out d minus 1c on the left-hand side, and that will give me minus a plus b d minus 1c, which is up to the sign the same thing that's in the equation. So overall this gives me minus d minus 1c, and I have a plus d minus 1c here. So another one down, one to go. So we have these vanishing immediately. And the rest I don't see immediately. I think there's a sign error somewhere. Yeah, there is a minus lacking. Wait, this is Anybody spot a mistake?
I think you multiplied the second row, second column with the first row, second column. So you multiplied the wrong elements.
Oh no. Hell. Okay. So I'm multiplying these, yeah? Times b plus d minus 1b. Oh, sorry. D. Thanks. Okay, so here we have our identity matrix, and then we have these two cancelling, and then I have minus something, and here plus the same thing, something. So we are reassured. Okay, as I said, this is once in a lifetime exercise. I just wanted to make sure at some point that I've tried it out myself. Sorry? Why is it a proof for one solution? Oh, and you think there could be other solutions? Well, the matrix inversion, if the inverse is unique, then this is going to be the only solution. Because the matrix inversion is unique. So if this is it, then it's not something else. And then you could not, I could use, so the way, the long form that I've written here is then the only form. So yes, you can switch around summons and so on, but you don't have any freedom beyond that. Okay, so this corresponds to sigma, and this corresponds to our precision matrix. And now we can use that. So element 1, 1 of my precision matrix is this part here. It's e to the minus 1. And that I can now write in terms of sigma. Yeah, so A would be sigma 1, 1, B would be sigma 1, 2, and so on. And importantly, what I wrote down here was P11 to the minus 1. Okay. So then we need this other term P21 times P11 to the minus 1. And that, if I use the equations from the other slide, I would write as minus f times e to the minus 1 times e to the plus 1, which gives me minus f. Okay. So equipped with these, we can now rewrite this term that's linear in y1 in the variables where we want to predict the response. Sorry. Yes?
Why don't you equate the derivative much faster than
Well, I did because I said this is the coefficient of the term that's linear in y1.
yeah, but instead of getting the second one, you can say sigma 1, 2 is equal to P1. So sigma 1, 2 at minus 1 is equal to P1, 1. And this gives you a resolution already. If you equate the second derivative, and then equating the first derivative, you get an equation for the limit. And that's done.
So how would you do it, Luca? You would?
So you need to say, you need to equate the first derivative because you need the several points, no, of the Gaussian.
Yes. Mm-hmm.
And then you would say, so mu1, 2 is equal to the derivative, to the first derivative of the exponent of the other Gaussian divided by epsilon 1.
Okay, I don't want to do it online now, but if you could write it down in detail, it would be great. Then I will report next time if it makes things faster. Okay. So the term that's linear in y1 becomes the following. I am using this here and substituting the expressions just found. So P21 times P11 to the minus 1 is given by this one here. And then P11 is given by that expression. Okay, and this time I'm also writing down the y1, which I did not do before. Okay, and then all of this I define as mu1 given 2, and that as sigma 1 given 2 inverted. Now we can insert this into the quadratic term just to make sure that also looks okay. So the quadratic term in y1 was given here. This is y1 transpose p11 times y1 again inserting the expression for p11 is and that happens to be the same as we saw in the previous equation. So that also is all right. Okay, and finally the term that does not depend in y1 can be adjusted accordingly so that it will simply enter my normalization coefficient. Okay, so that was exhausting. What we found in the end was that this statement here is true, that my conditional density of the y1s given the observed response as y2 is a normal with this mean and this covariance matrix. Okay, and this allows you to do, or I talked a lot about the distribution here along this line where the constraints meet, and what you see now are the equations for this one-dimensional Gaussian distribution, and in particular these equations also allow you to make more than one prediction at a time, so to get a Gaussian distribution in a whole subspace at the same time. Okay, now are there any questions? So where is it, or what applications justify the assumption? It is used it's an assumption which in itself is typically wrong, because most of the things that we look at are not joint multivariate Gaussian. But it turns out to be a very useful model, and the people who like this method, they write papers and then show on data sets they get better average performance and so on. Now, the performance that you get on average, I would say as such, it's a relatively expensive method, because when you have a big training set, you have this big covariance matrix or big linear system of equations that you need to solve. But I think it performs very well in practice, and in particular, this uncertainty estimate that you get out is a beauty, because you can use it to derive active learning criteria and so on. And this is also where it's being used. And then some of the semi-supervised learning methods also effectively use a Gaussian process inside. So I would say it's one of the broadly accepted methods that does very well. I would like, unless you have questions, I would like to use a few more minutes to give an outlook on extensions or what can be done with this. This has to do with the active learning. So you get out a prediction. So the prediction would be the OR grade, and you get out an uncertainty. And then you might want to drill your next hole where your prediction plus the uncertainty is largest, something like that. So where the potential gain is greatest. Some extensions. So one is that there is a Matern family of covariance functions that allows you to, well, choose the amount of smoothness that you want. So here, these covariance functions that I show, they have, well, somewhat different range, but mostly they differ in their behavior at the origin. And you get functions that are 0, 1, 2, or up to an infinitely times differentiable at the origin. So in one case, you get out this exponential decay. The other extreme would be Gaussian covariance. And you rarely see me use the font art feature of PowerPoint, but here you do, because there's a Wiener-Khinchin theorem which says that the spectral density of the associated stochastic process is the Fourier transform of the covariance function. So here, for instance, the high frequencies decay much faster when you use this covariance function than you use that one. Here the decay only is 1 over the frequency squared, and here they decay like an exponential, squared exponential of the frequency. Now here I've taken a picture from a talk by Rasmussen where he shows a couple of these covariance functions. You see they mainly differ here, and there are a few sample functions shown. So what does this model correspond to? So for this blue curve here, you get a very rough process. For the red covariance function, something that looks smoother already. For the black one, something that's even smoother. And then for the green one, really, really smooth realization. Now, what should you use? I think you should anyway use a nugget effect so that you don't interpolate your data and get these crazy overshootings. Especially in high dimensions, you're always data starved. So I think you would be well advised to not assume too much smoothness of your data and operate more on this side here. All of these functions can be expressed in terms of a single formula which was proposed by Matern, which involves the Bessel function. Then here's a comment on how can you estimate your covariance function. I here have an example from a paper that uses an ecological modeling paper. These people plotted the squared differences between two values over the distance of this pair of observations. And as expected, for if you have a smooth phenomenon for small distances, you get lower differences, and for large distances, you get larger differences. Now, if I look at these points, I'm not sure if this is a terribly good fit. You might even suspect some periodicity here. But anyway, this is the fit they obtain, and it highlights a typical problem, namely that you do not have very many observations that are extremely close together. So here the closest pair between any pair of observations is about maybe 80 units, or whatever these units are. And I repeated that what really matters is how your covariance function behaves here. So unfortunately, there's not much information in the data oftentimes as to what you should do here, and then this is a modeling decision. Now, this is for beautiness, what you can do, because you get out these mean squared prediction errors. Last time we talked about experimental design for the linear model, and I explained that now the way these squares are arranged in the plane, this is just artistic freedom, but here, for example, you have a square experimental area, or your feature space, and you're given by, I'm not sure, these are maybe 81 points or so, and if you fit a linear model, you would put all of your 80 points in the corners. Whereas if you now distribute your points in a fashion so as to reduce the mean squared prediction error, so averaged over your feature space, then you get out space-filling designs as shown here. And these numbers, by the way, so this is a design for 4 points, for 9 points, for 16 points, for 25 points, always on a square grid. And these number of points were chosen so as to favor a cubic configuration. So because the main point I wanted to make, and this is a picture from my thesis, that normally people, if you have 25 points to explore a square, well, you would put them, in this kind of arrangement, and that's good. But if you have, let's say, 49 points, then people would probably still put them on a square. But look, it tries to break the symmetry. It doesn't like this Cartesian lattice. And then as you go to more points, you really switch to a hexagonal grid in the middle, and then some transition region to the outside where it tries to approximate Cartesian lattice. And then the next question you can answer is, so what if we make our experimental region infinitely large, and if we have an infinite number of experiments that we can perform? Admittedly, it's a bit theoretical. Then you can already see here that at least in 2 dimensions, it tries to be hexagonal. But how about in other dimensions? And you can actually prove what the optimum lattices are in arbitrary dimensions. And it turns out that if you have a rough stochastic process, or if you have too few points to sample it well, then you should choose the best packing lattice. Whereas if you have many points or a smooth process, then you should use the Fourier transform, or the dual of the best packing lattice. And in 3D, for example, in 3 dimensions, those respective lattices are the face-centered cubic or the body-centered cubic lattice, but in any case, not the Cartesian lattice. Okay, so take-home message is that all of these people who do grid searches, that's probably sometimes including us, they use Cartesian lattices, and Cartesian lattices are just not good in high dimensions. So here there's just a picture in 2 dimensions, just a sketch to show how poorly the Cartesian lattice approximates, let's say, a packing or a covering problem, and how much better the hexagonal lattice is. And then you can ask in the best packing lattices and covering lattices are fortunately known in a couple of dimensions. These are studied by number theorists, so Sloan and Conway in particular. And as a closing comment, this thing about the rocket booster and so on, this was not invented. This was the application that Gramercy and Lee worked on. And this is an extension of everything that I've shown today, or a combination of what we've seen today with random forests and such. Because here, if you have this type of data, what you see here in black is a normal Gaussian process estimate with its uncertainty indication here. But looking at the data, it seems that there's less noise here and perhaps more noise on the right-hand side. And what this paper proposes to do is to build trees or multiple trees, and then in each leaf fit a Gaussian process. And then there's a lot of justification of how you can do this in a Bayesian setting and so on. But effectively here you get a couple of tree leaves, so there's a very weak line which probably doesn't come out well on the beamer. So in this 1D example, you effectively fit 3 different Gaussian process models here, and then they show that on a higher dimensional problem using rocket boosters and such. Okay, so we have seen 3 entrance ways to the wonderful world of Gaussian processes. The method is quite popular with machine learning people. The best book on the subject is by Rasmussen and Williams, which is also available on the web. So if you want to know more about this, it's Rasmussen and Williams, 2006, and it's called Gaussian Processes for Machine Learning or something to that effect. Okay, thanks for hanging in with this. Thanks.